Well, welcome class. I'd like to say that I miss you all right now, except for Leah, who's there operating the camera.
Hi guys.
And I'd like to go through what I'd like you to know about transition metal chemistry for the exam. First will be going naming and formulas. So something like this would be tris for 3. Ethylene diamine. Ruthenium 2 chloride. And it's the same protocol if you just had this. If you just had RuCl2, this would just be ruthenium. Ruthenium 2 chloride. I think the key point here is you don't have to write out the formula based on atoms. You just use the abbreviations for the various ligands. So on those first 5 pages on your handout, the first couple are the naming rules, of which if you go to about 6, you hit most of them. I'm not going to do any new stuff on you where you have bridging ligands, but I could do a little stereochemistry, which I'll talk about a bit later. You're going to see on the exam that I will give you that some of these naming things will be worth a lot of points. That's because there are a lot of things in here. It's like, okay, did you get the right term for 3 for a ligand that is chelating? Did you get the metal, the oxidation state? Did you properly write the anion? So there's a lot of things that I can grade on these sorts of things. I'll expect you to go the other way as well. So potassium. So straight up, just like you would write potassium carbonate, which is K2CO3, it'd just be potassium. Tetrachloral, so 4. You have 4 chlorine ligands. And you notice that the O is typically the thing you see with things that end with IDE. This is platinate, and you get the ATE because this is an anion as a complex. So if I help you there by putting the brackets around it. And then you put the oxidation state. So it's just a matter of practicing a few times. I got on the problem set, I have a few things for you to work on for naming for that. The next thing I have down on the great sheet of things I want you to know, what is the chelating effect and what is the macrocyclic effect? So this chelating effect is the extra stability you get when you have a ligand that can bind in more than one place. Generally, chelating is used most often with two. So this is more stable than this, even though pretty much the ligands are pretty much the same. And I always think of this in terms of cats. So this is like having two cats rubbing up against you, and you need to leave, and you got to kind of get the cats away from you. Well, you get one cat away, and it goes, and then you can kind of work and get the second one away. You get something chelating, get the one away, and you still got the other one rubbing on you. Well, when that one is still there, you finally get rid of it. Oh, but the other one's pretty close by, so it can start rubbing up against you again. So the thing that gives it the extra stability is you have the ligand localized around the metal, so you have to get the second one off while the first one of the atoms is a little bit further away. Now, to even exacerbate that some more, what if all the ligands are hooked together in one big cyclic thing? So if you break this, that even restricts the amount of movement this nitrogen has to come back, and it's pretty hard to get rid of all of these, and that provides a lot of stability. A classic ligand for that is porphyrin, or as it's said as a ligand porphyrinato. And that's why our bodies use that so much for the support for iron in the various heme-based enzymes. The next grand task is calculating ligand field stabilization energy. And there are a lot of steps to this, and I can ask questions about each step independently. But if I give you the full calculate the ligand field stabilization energy, here is potassium trisalloxylato manganese, and I'm going to hold off on the oxidation state because we have to go through and determine that. So the big thing about ligand field stabilization energy is we're always going to do this for octahedral compounds. The first thing we have to do is determine the oxidation state of manganese. So we have to go to our cat chart. So 2, 1, and 3. Charge on potassium is +1. The oxalato ligand is -2, so that's something you'll look at your list of ligands and you'll see that. So this is -6, this is +2. To get this to be 0, because it's a neutral compound. This has to be +4, so we are dealing with manganese 4+. Now that we have the oxidation state, we need to get the number of d electrons. Manganese is group 7. Plus 4 gives us 3d electrons, so this will be manganese. D3. Now, coordination number, since it's octahedral, coordination number is going to be 6. You'll need the d orbital splitting pattern. It's 3 down, 2 up. There's an energy scale here. And we'll put in our three electrons. The formula is minus 0.4 n delta O plus 0.6 m delta O. And our delta O is our ligand field, so it's the energy from here to here. So we would say the ligand field stabilization energy here is minus 1.2 delta O. So always remember the delta O. That term always needs to be there. What if I had a 3D4 system? Well, then we have to consider the question, is it going to be high spin or low spin? High spin will be up here. And low spin you'd pair up and then do the same sort of calculation. I'm going to just take the step over here to look at the list of things I've asked you to do. Make sure I'm covering them all. Okay, looks like I'm okay there. Here are the coordination numbers. So I'm going to limit you to 4, 5, and 6 for coordination numbers. Coordination numbers is how many atoms are attached to the metal. So for a chelating ligand like oxalato or ethylene diamine, you get 3 of those. Each of those can coordinate using 2 atoms. So you get 3 times 2, 6, and that'll be octahedral. For 4 coordinate, you get your classic tetrahedral, which I'm going to abbreviate TD, and then square planar. For 6 coordinate, I'm going to just stay with octahedral. Five coordinate will be square pyramid. And trigonal bipyramid. Most of the time we will be looking at the square pyramid. And you get this when you have multiple bond ligands, usually oxygen and nitrogen. And you get those as an axial ligand, and it'll be surrounded by a base of 4 other ligands. So you'll need to know these geometries. You'll need to know the 2 splitting patterns for 4 coordinate and the splitting patterns for 5 and 6. So the d orbital splitting patterns. For tetrahedral, you'll have 2 down, 3 up. And you have an energy gap, delta T, much smaller than octahedral. You will also see some 4 coordinate square planar compounds, and you have a delta square planar. 5 coordinate, you're going to have this 1, 2, 1, 1 pattern, and octahedral will be the 3, 2 pattern. So you'll need to know those d orbital splitting patterns. I'd like to now thank our sponsors, Visionary Medical Supplies, for allowing us to do this in their facility. You see this great big molecular orbital diagram for ferrocene, and you go, oh my gosh, what is this about? If you look at the place where it's kind of squared off, you see this thing T2G and EG. If you look at the big molecular orbital diagram, this T2G is essentially non-bonding. EG is antibonded. There's similar things in the 4 coordinate and 5 for 5 non-bonding here. Pi antibonding here and a couple sigma antibonding here. And antibonding here is sigma antibonding. Square planar. Pretty much all of this is non-bonding, and this is a big, nasty sigma antibonding. Tetrahedral, essentially these are non-bonding, and these are sigma antibonding. Okay. Now, let's talk about strong and weak field. When will you have a strong field? We're going to look first at 6 coordinate. Strong. Ugh. 4D or 5D metal. No matter what they're with, they're going to be a strong ligand. They're strong metal. It doesn't matter what the ligand is. Strong field. If you have a 3D metal, then you have to consider the ligand. Strong ligands typically are like cyanide, CO. Then you have something like ammonia. That's kind of in the middle. Then over here, you have your weak ligands. You're going to have to be able to explain why these are in this order. And this is based on something that has experimentally been derived called the spectrochemical series. So that is a quantitative measure on how strong a ligand there is. What's the experimental evidence we have for ligands being strong or weak? Well, first we have magnetic. So you can determine the number of unpaired electrons through a measurement called magnetic susceptibility, and it works pretty well for 3D ligands, or 3D metals with ligands. The other thing you can look at is visible spectroscopy, and if you get a transition from a lower state from the T2G level to the EG, and you are sure of that, you can look at the wavelength of light, and shorter wavelengths of light will have higher energy. So we can experimentally get a handle on how big this gap is, whether it's strong or weak. With strong systems, 6 coordinate, you get low spin. With low spin, you have a large delta O. So if I have a D5 system, 1, 2, 3, dramatic pause, 4, 5. I have one unpaired electron, and if I take an electron from the EG, or T2G to the EG, by the wavelength, it can tell you something. Short wavelength, large energy, and you can actually calculate the energy gap here. I'm not going to have you do this, but I want you to be aware of this is how we experimentally determine this. weak field will be high spin. The delta O will be much smaller, so I'm going to actually indicate that.
Do you want to use the darker blue? The one you have is just a little bit light. Thanks. Oh yeah, that's good.
I'm going to again do it for a D5 system. So there'll be one electron in each, and you can, using magnetic susceptibility, determine that we have 5 unpaired electrons. Okay. And you can also use UV spectroscopy to see that you're at a much longer wavelength and less energy for this gap. Okay. 4 coordinate. Tetrahedral will be the weak case. So all the weak ones will be tetrahedral, and there will be a few exceptions I'll talk about in a minute. So tetrahedral high spin. So if I do a D5 case, here we go. Strong field will be the square planar. Low spin. So, strong field. Now you may be asking, why did you do 8 electrons this time? You've been doing 5, for examples. Almost all the time, when you do low spin 4 coordinate, you will have D8 systems that are square planar, unless you have some ligand that forces that square planar geometry. So almost all the time, if it's D8, you go, ooh, this might be a square planar. And strong field.
Action.
So we just had to trade out a little bit of recording. So we picked up here again, coordination number 4, and I CO4 tetracarbonyl nickel 0. this is nickel. It's argon 3d10. We have a strong ligand. But the geometry is tetrahedral. And you go, wait, you just said coordination number 4, strong ligands are square planar. Why is this tetrahedral? This is due to this being 3d10. Ligand field stabilization energy, which I've only asked you to do this for octahedral, but you could do this for square planar and tetrahedral, is equal to this number. It's one of my favorites. 0. If you don't have any ligand field stabilization energy, and you get that in cases of D0, high spin D5, and D10. The shape of your compound, or the geometry, will do what's advantageous based on valence shell electron pair repulsion. So it acts just like a main group. Now, if we go back and think about it, hopefully you're not surprised by this, because part of your exam will also be on periodic trends. And remember the n plus 10 rule, where n is the group number, okay, group number, not the atomic number. So you got to look at the group number. And I said this works really well when things are in their highest oxidation states. With transition metals, generally this will be D0. Like for zinc and magnesium, it's D10. And the big thing is you don't have any ligand field stabilization energy. So everything is governed by sterics. So valence shell electron pair repulsion rules apply. Now I'm going to address a little bit about what makes a ligand strong or weak. I'm going to take a metal, have ordinary garden variety, sigma only, so just donating one lone pair, and I'm going to replace those ligands with something that is quite strong. Like cyanide or carbon monoxide or the carbonyl ligand. So what's happening here? Well, if you look at some of your handouts, or your next set of handouts, what's happening, your EG level is staying the same, but your T2G drops. Because it's interacting with the ligands through one of our favorite mechanisms, pi back bonding. So the d orbitals that are in the T2G level interact with the pi star orbitals. So you go look back in your notes on bonding and see what those look like. So things that can pi bond, pi back bond, that have pi bonds in them, they lower T2G. What if I replace my ligands with something that's a stronger sigma donor ligand? What happens? My T2G level stays the same, but my EG level goes up. And remember that the EG is sigma antibonding. So you have corresponding sigma bonding that's becoming stronger and going lower, and when that goes lower, the sigma antibonding goes higher. So for strong sigma donors, this is what happens. EG goes up. So generally things with more electron donating groups, chelating ligands are better than the monodentate, just where you have just one atom ligands. Those things will drive up the EG level. And that's why they tend to be more low spin. What happens when I have weak ligands? Things like water, halides, hydroxide. If you look at those, they have multiple lone pairs. One is going to form essentially a sigma bond, and the other lone pair is going to start donating some of that to the metal. And what happens? Your EG stays the same, and that drives up your T2G. So if you look at some of those pictures that are in your handout, it kind of shows how these orbitals interact. But the thing you need to know, weak ligands, T2G goes up. Strong sigma ligands, EG goes up. Things that can pi back bond, the really strong ligands, T2G goes down. Now to review the things we have to consider, the things that will increase delta O, so a more strong field. For 4D, 5D metals, strong. Stronger ligands, like cyano and carbonyl. The last thing, you've been waiting for this. It's one of the big things, and it's not size. Charge. So if we're making a comparison where we have the same metal, higher charge, larger delta O, so higher charge. Time for a little snack here. Oh my god, flaming hot Cheetos. How can you eat them? Holy cow. Woo. Man, I gotta take a hit of coffee here. Once again, I'd like to thank Visionary Medical Supplies for use of their facility. With our transition metal compounds, we can have isomers, so stereochemistry. So not just organic, we have some too. We can have cis-trans. I'm putting charges on just to make things clear. As you may surmise, cis-trans. Meridinal, facial. So if we have three of the same ligand, and if they're all in the same plane, or a meridian, that's the meridinal isomer. Fact is if they're all in the same face. Now with meridinal, it's also possible if you have a second ligand. You can have that cis or trans. Delta lambda. That's when you have enantiomers. So it's the moral equivalent of R and S. Now the happy thing, probably for you, is I'm not going to have you figure out which is which. And I'm not going to have multiple metal centers. So you're not going to have RR, RS, SR, and SS, and things like that. Almost all the time with delta and lambda, you will have at least 2 chelating ligands. Usually 3, but often 2. So here I'm going to represent this to be something like ethylene diamine or bipyravil or any other chelating ligand. And here you can see that if I put a mirror plane here, these are non-superimposable mirror images. Before I did the cis dichloroisomer, here I do the trans, and you don't have delta and lambda with the trans. Are you ready? There's an internal mirror plane. So if you remember a little bit about organic chemistry, you have mesoforms. That's a moral equivalent here. You have an internal mirror plane. Here's a ligand, thiocyanate. It can form linkage isomers. The question is, which atom is going to bind to the metal? Sulfur versus nitrogen. Here's your answer. Silver will like to go after the sulfur, titanium, the nitrogen. What is this a reminder of, Abigail? This is where hard, soft, acid-base theory comes into play. The soft sulfur goes after the softer silver. The hard nitrogen goes after the hard titanium. So linkage isomers, what atom actually attaches to the metal when you have a choice? Why do we have this? With ruthenium, we have this. Just had a little break there, and I had another flaming hot Cheeto and had another hit of coffee. Size matters, especially for larger, weaker ligands. This would rather be FeCl4 2- plus 2 free chloride ions, while this would rather have all the chloride ions be attached to the ruthenium, because ruthenium is larger than iron. So we had one where charge, hard soft acid base theory, size matters, all those things still apply, and they're things that we have to consider. I'm going to talk about some compounds that are made out of my favorite ligand, porphyrin, the porphyrinato ligand. It is a 2- ligand. It is a macrocycle, and 4 nitrogens bond to the metal. So I'm going to represent porphyrin as a ring. I'm going to use my favorite compound, metal triple bond nitrogen, so a nitrito as it's called. So if we have chromium, manganese, and iron, nitrito here is 3-. Chromium is a D1, manganese D2, iron D3. I look at the IR and look at the stretching frequency. Chromium is about 1,000 reciprocal centimeters. Manganese is about 1,000. Iron, 800. Weaker bond. Weaker, weaker, weaker. In fact, you have to isolate this in an argon matrix. So you have to go down to the freezing point of argon in order to actually observe this species. And it's very, very reactive. In fact, it forms a dimer. So if we look at the splitting pattern for the 5-coordinate, non-bonding down here, pi antibonding here, and these are both sigma antibonding. 1 electron. Okay. The stretching frequency here would change if we put something here. 2nd electron goes in there, no issue. 3rd electron, suddenly we are occupying a pi antibonding orbital, and we see the strength of the bond decrease because of that. What you'll see a lot of is the square pyramids with things like nitrogen or oxygen up here. Very high oxidation state metals, generally because you only want 2 electrons, because if you put in that 3rd, you're going to start to occupy antibonding orbitals. Next, something called the Jahn-Teller effect. So I'm going to do one for an octahedral compound. And now we have to consider which particular d orbitals we're using. So down in the T2G level here, dxy, dxz, dyz, and the upper ones here, dx squared minus y squared and dz squared. This shows up a lot for D9 systems, although it's possible for a lot of others. But it has some really big implications, especially for copper 2+, which is D9. And this can work with either tetrahedral or octahedral compounds. The Jahn-Teller distortion comes about because you have unequal occupancy in some orbital. Something with 1 is not as good as something with 2. So what happens is the less occupied orbital, fewer electrons, will go up in energy. So this is your original energy level. One will go up, one will come down. There's an energy advantage here when you send something with just one electron up to a higher energy level. So essentially what you're doing is you're gaining 1 electron's worth of energy, so I'll put that in quotes, by dropping this down here. You may be asking, does this happen in the T2 level as well? It does. So if I call this the dz squared going up, anything with a z will go up, and anything that's just xy will go down. And the amount of drop in energy and the amount of up in energy will be the same. Since these are all equally occupied, you don't get any energy advantage here. So you look for the energy advantage where you have unequal occupancy. What is the physical phenomenon that you can see? If you look at bond.
Okay. We left right there with when you were talking about the D9.
So we're going again?
Yep.
All right.
Yep.
All right, so we had another time limit here. And I think we left off with, okay, what's the physical phenomenon that we can observe? Well, what you will see for an octahedral compound is you will have a distortion from an ideal octahedron. You know, 2 of the ligands will be a little further out, and 4 will be a little further in. You often see this with copper in a tetrahedral, where instead of seeing a perfect tetrahedron, you'll see that distorted. And that's an indicator that you have this Jahn-Teller distortion. Biologically, this can help mediate what the oxidation reduction potentials are. So you can regulate that by what ligands you have around there, and then you have this little bit of distortion that can change their redox potential. So that's the end of the list. So you're probably wondering, what's the plan going forward? I am going to assume we will not see each other in person again as a class. So, this next section on periodicity, main group chemistry, and this transition metal chemistry will be the next exam. So I'd like to set that up for a time after your problem set is due, and then I can have comments that I'll send via email. And I'd like you to pick a date sometime after that. I will email the exam out. This will be a timed event. I won't have any restrictions on what you can use, but remember, it's a timed event. So if you think, I don't have to study and I can just look everything up, you're probably going to be in trouble. I will also send the assessment quiz one last time, and just one last time. You have 2 hours to do both of them. I will keep track via when I send it out and when I get an email back from you. If this is a problem, please let me know. The best way to get a hold of me, if email is an issue, and you can just call me, I'll give you my cell phone number, 608-807-6927. I don't always have that on, so I might not pick up right away, but I can, email or text you back. Okay. Right. The grading scale I have right now is off the board. I don't know how this is going to work. I'm going to use what I have as a guideline, but I'm going to make the cuts however I think is most fair. Okay. So there's the change in the syllabus. Okay. For the bioinorganic section, I already sent out a problem set. You can work at that in your group. I will have a project for you. I will send via email after you agree on the time you want to do the exam. I will have that absolutely due as a hard deadline will be May 11th, which will be the day we would have the final normally. So that will replace your third exam. Okay. If you have any questions, because I know I misspoke and had to double over myself a few times, please email me for any sort of questions you have. And if I get enough questions and you have something you want to go over that I don't think we can do effectively by email, I'll come back and make another one of these videos. So I'd like to thank you all for putting up with this. Thanks again to Visionary Medical Supplies for letting me use the facility. Frito-Lay for flaming hot Cheetos. And this little weight to keep my blood flowing. So hope to hear from you soon via email and answer any questions. And propose a date for the exam and I can set that up. Thank you, and I do miss you, and stop by again once this is all over.